Hello there. In this problem, we have a rope which is sliding through a hole on a frictionless table. The rope is uniform, it has some mass capital M and some length capital L, and initially the rope is stationary with some initial length L naught through the hole. So to tackle this problem, let me go ahead and start by putting the origin of our coordinate system here at the hole. And what we're going to track is we're going to track the amount of rope which has fallen through the hole, and this is always going to be at some height z. And we're going to indicate downward as our positive direction. Alright, so at any given moment in time, the net force on this rope is going to be based on, well, how much rope is actually through the hole, right? So if I have this chunk of rope here through the hole, the rest of this guy here, this is supported by the normal force of the table, right? So it's only the bits of rope through the hole that are going to be getting pulled down by gravity. So this is going to be M through the hole times G, right? That's going to be our net force on this rope here. Let's go ahead and write out M hole explicitly though real quick. So M hole, how do we get that? Well, let's go ahead and take the mass density of our rope, which involves taking the total mass of our rope, M, divided by its length, L, because this is just a uniform rope. We just take the total mass divided by its length. Now just times the length of the rope that we're interested in. Oh, that's just Z, right? This length Z here is the amount of rope which is through the hole. So this is going to tell me the mass of that section of rope. Okay, and now this is times G. Right, and so now let's go ahead and just write out Newton's second law. So what's our net force on the rope? We already wrote it down. mg over L times Z, and this is going to be equal to ma, or the total mass of my rope, times Z double dot. Now there's one important subtlety here that we need to point out, right? Because when I write out Newton's law like this, right, we know that net external forces causes net accelerations of what in a system of particles? The center of mass of that system of particles, right? And, one thing you might say is, well, if I look at this system of particles in my rope here, right? Of course, the center of mass is going to be moving down as I get more rope dropping down here for sure, but the center of mass is also moving to the right, right? As this rope is sliding. And yet you're claiming that we only have one net external force downwards here, and that's accelerating just this Z direction. That doesn't make logical sense, right? Right, so what I'm going to point out is the thing that we're kind of missing here is we're missing out this kind of geometric effect here when this rope is actually falling through the hole. There is this an additional force here, a contact force, right? Which I'm not including. It's kind of a constraint type force, but that's what's responsible for actually causing this horizontal acceleration for my rope center of mass. But that's fine. Let's just keep things simple and just track the coordinate that we're actually interested in. Right, so now if we have this differential equation here, let me go ahead and cancel out m's. Let me go ahead and write this out in its glory, right? I have d squared z dt squared minus g over lz is equal to 0. This is a pretty common differential equation, right? We're going to use the Ansatz z is going to be something like e to the alpha t. Okay, so let's go ahead and try plugging this form in here. That's going to give us alpha squared e to the alpha t minus g over l. E to the alpha t is equal to 0. These guys cancel. Right, and so we're going to get two solutions for alpha. Alpha is equal to plus or minus root g over L, and these correspond to our two linearly independent solutions of this differential equation. Right, and so let's go ahead and write out the general solution together here. We're going to have z as a function of time is equal to c1 e to the root g over lt plus c2 e to the minus root g over lt. Right, it's a general solution. We have these arbitrary constants c1 and c2. But we're told two things, right? That the rope starts out stationary and it starts with some initial length L naught through the hole. So let's go ahead and use these facts, okay? So let's go ahead and use the first fact that we have some initial length L naught through the hole. So Z at T is equal to 0 is going to be equal to L naught. Right, and so to be super clear, I'm plugging 0 in for t in this equation. E to the 0th is always going to give me 1, so I have c1 plus c2 here, right? And next, right, the next condition is that this rope starts out stationary, so the velocity, right, or z dot at t equals 0 is going to be equal to 0. And so we're going to have, this is going to be equal to, take the derivatives and plug in 0 for t. You're going to go ahead and get c1 times root g over L minus c2 root g over L. Right, and so can we go ahead and read off the relation between c1 and c2 here? Yeah, almost immediately, right? From this bottom equation here, this is really just a fancy way of telling us that c1 is equal to c2. Let me just go ahead and call that, this fancy c for right now, right? So that really means that this top equation here reduces down to 2 times the fancy c is equal to L naught, right? And so to just be super duper clear about this, our conclusion here is that c1 is equal to c2 is equal to L naught over 2. Okay, great. So let's go ahead and plug these in for c1 and c2. And I'm going to go ahead and kind of write this out a little bit suggestively here. Okay, so I'm going to write this as L naught times e to the root g over lt plus e to the minus root g over lt all over 2, okay? And the reason why I'm writing it out this way is because this guy here, this guy is the form of a hyperbolic cosine function, okay? And so this, in fact, reduces down to L naught times hyperbolic cosine of root g over lt. So the motion of the rope as it falls through the hole is actually described by a hyperbolic cosine function. If you enjoyed this video, found it helpful, let me know in the comments and consider subscribing to the channel. I love to hear about people getting on board. But other than that, thank you so much for watching.